Alright guys, so we're going to pick up today with lesson 2, which is going to be weather systems. Alright, hopefully you all have turned in your vocabulary. Hopefully that wasn't too difficult, and just like we did yesterday, if you need to hit pause so you can fill in your notes as you're going along with this, make sure you do that. That way your note set is complete. Also, if there's any concept that you're like, wait, he went a little fast, just hit pause or rewind, go back a little and listen to it a second time. I will definitely review all of this stuff on Thursday. All right, so yesterday we talked a little bit about wind, and here we have a focus of why do winds blow in the direction they do. Now this one, unlike some of the other focus questions that I'll look at, we kind of already know this answer, right? Because we said that when we have cold air that is high pressure, right, that cold air that's high pressure is going to move toward warm air that is going to be low pressure. And just to recap what we're talking about there, it doesn't hurt to say it numerous times. Warm air rises and cold air sinks. So the sinking air creates the pressure pushing down, and therefore it's got to go somewhere, so it's going to go where there's less pressure. So a quick overview of some of the vocab we're going to need to know for this. So again, you hopefully have turned in your vocab, but the Coriolis effect, polar easterlies, prevailing westerlies, trade winds, jet stream, and front. By the end of this section, we should see how all of these different terms really help us to understand planetary winds. All right, so you're probably thinking, what exactly are planetary winds? Well, if you think about us having the Earth, right, we have the equator at the middle, then we have 30 degrees, 60 degrees, and 90 degrees. I'm going to go back and label those 90, 60, 30, and 0. These are all north latitude. And in fact, we're going to have areas where the air is going to sink. That's going to be around 30 and around 90. That's going to create high pressure. And then at the equator, we're going to have rising air, which is going to create low pressure. And over time, what actually happens is you get these surface currents that we're going to see are going to move down this way, move up that way, and then again move down that way. And this is where all these fun terms, polar easterlies, westerlies, come in. All right, so you'll see that in a minute. I've kind of gotten ahead, and again, this is one of those things that on Thursday I'll draw on the board, all the fun markers, and we'll have a really good sense of what we're looking at. Quick reminder about convection, right? Warm air rises and cool air sinks. So cool air sinking and warm air rising. And so warm air coming across, cool air sinking and coming this way. And the big idea is that you get this big convective mixing process. Okay? We have mantle convection, we have convection in fluids, and we're going to see today how convection actually happens in the atmosphere. So, we just looked at the quick sketch on planetary winds, and this relates back to Earth's winds. So here it says the direction of Earth's winds are influenced by Earth's rotation. Now, Earth rotating, if you think Earth rotating counterclockwise, then we're going from west to east, and that rotation then, if an object is trying to move vertically on the Earth's surface, it's going to get deflected, or its apparent path is going to get curved because of this Coriolis effect. So you probably want to hit pause and fill in some of the important points here on the Coriolis effect, like the apparent curved path rather than a straight line. But I'm going to actually sketch in for you this idea that if you're on the Earth and you're at the pole and you decide to throw a ball toward the equator, by the time it gets to the equator, it's going to hit a point that was further behind because the equator is trying to move in the east direction. So by the time whatever wind or object is moving toward the equator, it will actually hit a path to the right of where you're going. Now, the Coriolis effect is way more complicated, and I don't kid when I tell you that my sister, who is a couple years older than me, is still flabbergasted by the fact that I teach earth science because she struggled with earth science, and it was the Coriolis effect that she could just never wrap her head around. All right, anyway, enough about my personal life. Let's keep going. So, the Coriolis effect is going to deflect winds to the right in the northern hemisphere and actually to the left in the southern hemisphere. We'll get into that a little bit later. But remember that winds are moving from areas of high pressure to areas of low pressure. All right, let's kick it up a notch here. If Earth's heating was not impacted by the rotation, so just imagine that we were on a planet that didn't rotate, well then you would just have two convective cells. You would just have cold at the poles and warm at the equator, so high pressure coming from the poles going to the equator. And that's what this diagram here is trying to show you guys. But in fact, we know that the Earth does rotate, and in fact, along the equator, we're moving at about 1,670 kilometers per hour. Now that's really fast. If you think about being at the poles, you could spend an entire day standing in one spot because the pole is going to be super boring, right? You're really not having any displacement there. You're just standing there as the world turns below you. But along the equator, you have to cover 1,670 kilometers each hour in order to complete the over 40,000 kilometers of the circumference of the equator. So therefore, you have more distance to cover. You're going to have to move faster. Okay, let's kick that up a notch again. Right? When we look here, we can see that as you move toward the pole, your rotational time is going to get slower and slower. So if I have a parcel of air that's moving from the equator going toward the poles, it was already accustomed to moving faster to the right. And that, again, is part of this Coriolis effect idea that winds are going to curve to the right as they move from the pole, as they move toward the poles. Let's stop with that thought for now. So this slide actually depicts exactly what I'm saying, right? Because the air mass that is moving from the equator up toward 15 degrees north latitude, there's going to be an apparent deflection to the right. And this is really what the Coriolis effect is all about. So, large scale, we can get deflection to the right in the northern hemisphere, deflection to the left in the southern hemisphere. And this diagram shows you both when you go from the equator toward the poles and what you're going to get in each hemisphere. Definitely need to know this stuff, folks. So then we get to put some names to these ideas. So winds that are going from the poles to the 60 degrees north or 60 degrees south latitude are referred to as polar easterlies. Now, we're going to see that when we get winds coming from the lower region and moving up toward the poles, this is where we're going to get our westerlies. So we're going to get a boundary between those polar easterlies and the prevailing westerlies, and that's where our polar front is going to occur. And that really is your 60 degrees north, 60 degrees south latitude. So I know you guys got to fill a bunch of that stuff in. Again, feel free to hit pause, make sure you fill it in, and then when you're doing the homework, really try and zero in on these things. It's going to pay huge dividends. All right, now, when we talk about prevailing westerly winds, we're talking from 30 to 60 degrees north latitude. This is going to be the primary source of U.S. weather. All right, so steady winds that move much of the weather across the United States and Canada. It's a pretty big deal. So then what's the significance of the 30 degrees north latitude? There at 30 degrees, you have high pressure, you have cooler sinking air. And so when it comes down, it either is going to have to go north with your prevailing westerlies, or it's going to go south toward the equator as your trade winds. And so your trade winds end up being these winds that are coming down toward the equator. And what's really, really cool is because you have that sinking air, you actually develop a specific name there called the horse latitude. So you're not getting an east-west curvature to the wind. Instead, the air is sinking straight down. And so what actually happened is that when ships got caught on the horse latitudes, back in the day, they were reliant on wind in order to be able to move, right? They're big sailing vessels. So when the air was moving vertically up and down or just coming down, the ships would get stranded there for days on end. And one of the things they would do is, unfortunately, have to turn around and eat the horses or throw them overboard in order to lighten up the ballast on the ship and try to get it to move. All right, that was way more than you guys needed. I apologize. Kind of going off the deep end with some of that stuff. All right, near the equator, trade winds from the north and south join together. All right, and this is what we refer to as a convergence, right? So to converge, like two armies converge on a battlefield. Not the first time we've used the word convergence, by the way. But when they come together, this is where the intertropical convergence zone occurs. And that's where you have winds that are coming from the north and the south converging together, and we can actually get some moisture developing in those areas. Now, this brings us back to all of these fun terms that I've been talking about, and this makes a really great diagram. You see the polar easterlies, you see the prevailing westerlies, and then you see the trade winds. And realize that we can label them north and south. So you have the northeast trade winds, southeast trade winds, your westerlies. And then, before I talked about the highs and lows, so you have your subtropical high, you have your polar high, you also have your equatorial low. And these are all different markings at your latitudes that will determine whether the wind is going to move north or south. Is it coming toward that point, or is it moving away from that point? So just a quick side note, winds are named from where they come from, right? Just like if I got on a plane and I fly over to Germany or over to Holland, they're not going to turn and be like, oh, Mr. Weaver is Dutch. No, they're going to turn around and be like, oh, he's an American, right? Because they're going to describe me based on where I come from, not necessarily where my ancestors came from. In the same way, winds are named for where they come from. So if the winds come from the west and head to the east, we say that it's a westerly wind. If winds come out of the north and go to the south, we're saying that you have a northern wind or a northeastern wind in the case of some of the curvatures that we would have. Then we get to the jet stream. And the jet stream gets a little more complicated because here we're looking at a band of fast-moving air. Usually sits a little bit higher in the atmosphere, but to sum it up briefly, you basically have this stream or there's this constant flow of air in the atmosphere, and with that, we're going to see the effects of the jet stream in weather, right? So when the jet stream dips down from Canada, this time of year we get these polar vortex. We get these colder dips in temperature, and when it flexes up, then we can actually have some days of warmer air, right? So minor jet streams are subtropical jet streams, right? That's just getting a little technical for right now. I'll expound on that when I see you guys on Thursday. Just to wrap this all up, storms fall along jet streams and can generate large-scale weather systems. So when we pay attention to the jet stream, when you look at the forecast this time of year, it'll actually show you where the jet stream is, and if it's dipping down, what the effects are. If it's pushing up, what the effects are. Now we finally get to fronts. So fronts are bringing back the idea of air masses, which we discussed the other day. And an air mass, we said we could have a warm, dry air mass. We could have a cold, dry air mass. So when you have two air masses that are coming into contact with one another, there's going to be a boundary. And that boundary is what we refer to as a front, right? So that's a region between two air masses of different density. Now, you may have heard about a cold front moving in or a warm front moving in. When a cold front moves in, we're going to see that we're going to have cold air behind, but it's going to actually push up and out the warm, moist air. And that's where my favorite cloud, if you remember, the cumulonimbus cloud, will end up forming. And you're going to get some heavy rains, you get those strong winds. So it's a lot of fun. That's where we can get some cool thunderstorms. But we're going to get into that in a second. So now as you go through what I just described to you, now you see in a picture. Cold air mass pushing in, warm air mass getting bulldozed up and out of the way, creating that cumulonimbus cloud, and then you get the heavy precipitation. Right, so again, this is a cumulonimbus. Cumulonimbus cloud, right? And that's going to have heavy precipitation, and I would even expect some lightning if conditions are really good. All right. Now, go ahead and take a second and fill in what it says in those notes so that you understand, right? When cold, dense air displaces, meaning forcing upward warm air. It forces the warm air, which is less dense, up along a steep slope. And that's what I said was the bulldozer, the steep slope. Think about a bulldozer coming in. That's almost a completely flat, almost 90 degrees panel that pushes soil. So here we have this sharp angle that's forcing the warm air up and out. But wait, there's more. Here you guys can see a warm front moving in. Now a warm front gradually overtakes a colder air mass, or basically replaces that colder air mass. And as it does that, you can actually get clouds forming and steady, kind of annoying precipitation to follow. Right? So you're going to have warmer temperatures. You notice, I forgot to point out before, the symbols are on the left. So over here, you can see they look like little suns on the front of the line, and it shows the direction that that air mass is actually moving. So there's your cold front symbol. Warm front symbol. I'm just going to pull down for a second. Here you can see the cold front symbol. Right? It looks like little icicles. Those will be testable items. Right? Make sure you can identify them. All right. So two fronts out of the way. Let's keep going. What happens if a cold front can't overpower a warm front? Well, in that case, you end up with a stationary front. And the stationary front, you can actually tell from the symbol, looks like a warm pushing against a cold. That's why you have the alternating sides. And basically you have these air masses that have now stalled. And if you're thinking, like, why would it stall? Well, just because you have a cold air mass and a warm air mass doesn't mean that there's a huge difference in temperature all the time. So if the temperatures are relatively close, you might not get that power from the warm front or the or the cold front to push the other one out of the way. So think close range in temperatures and the stalling or not moving of an air mass. So we might get the same weather for an extended period of time because of this phenomenon. And then we get to the occluded front. Now, when I think about an occluded front, I think warm air mass was trying to overtake a cold air mass. So you had a warm front going on, and then another cold air mass pushed in behind even faster. And they basically merged the two cold air masses, which you guys can see down on the bottom. Over in here, you got the two cold air masses that have now sutured together and picked up the warm air mass. So now the warm air mass is basically piggybacked on top of the two colder air masses. So that's what we call an occluded front, right? The warm air mass has been separated from the ground surface and is riding on the backs of two cold air masses. And here, think about what would happen if I took the symbols of a cold front, blue, and a warm front, red. When we blend the two together, we end up with this purple, and you see that rather than the stationary front, which you had alternating sides, now you have an alternating symbol on the same side. So again, these symbols are pointing in the direction that the air mass is moving. Right, the air mass is moving this way, or the air masses in this case are moving that way, and you get those alternating symbols. So a couple points I just want to hit home on. The diagrams that you just saw of each front, definite quiz test material. If you haven't figured out, and now it's February, I love diagrams. Right along those lines, the air mass diagram, right? I'll give you a picture of the U.S. and I'll put letters over the central U.S., this up in like Canada, and then over the ocean, like the North Atlantic, North Pacific, or down around the equatorial region. And you should be able to tell me if it's maritime tropical, maritime polar, continental tropical, continental polar, and then we also have the Arctic up in the tundra up by the pole, like the polar region. So be ready for that. Don't worry, I'll give you that diagram when we're together next. Now let's take a second to come back to this idea of pressure and pressure systems. So we remembered that due to the Coriolis effect, we can have high pressure go to low pressure, and in the northern hemisphere it's going to curve to the right. If we have low pressure, and then we have high pressure, high pressure, high pressure, high pressure, well, the winds are going to curve to the right, curve to the right, curve to the right, curve to the right. You're like, okay, why did he just do that? Because this is actually what creates the counterclockwise rotation for hurricanes in the northern hemisphere. Tornadoes, similar phenomenon where we're going to get this counterclockwise rotation. And this counterclockwise rotation occurs because you have a center of low pressure and high pressure air is trying to push into that low pressure. I think about this like a vacuum cleaner. Again, the air is being drawn up, creating a void underneath, and more material gets pulled in there. The opposite of that would be if I have a center of high pressure, that would mean that I have low pressure all around. And therefore, winds again are going to move outward. But now this is going to create a general pattern of clockwise rotation. Now, I always encourage you guys to draw out the little things that I talk about. But when you do that, I would put these letters with it. Hawk and lick. And lick and hawk are ways of remembering that when you have a center of low pressure, air is going to move inward, and you're going to get counterclockwise rotation. lick. When you have high pressure, winds are going to move outward, and you're going to get clockwise rotation. So that's your hawk. Now I just gave you a quick overview of what we're talking about. Now, let's actually see what the notes say. Here it says, sinking or rising air, combined with the Coriolis effect, that was the curving to the right, results in the formation of rotating high and low pressure systems in the atmosphere. Air always flows from an area of high pressure to an area of low pressure, and we just reinforce that. So I'm hoping this little sketch helps you to understand the concept. Now let's see it in picture form. All right, area of low pressure, winds are moving inward, curving to the right, creating counterclockwise rotation. The area is rising up. All right, so here, just to bring it back, we just said we have lick, L-I-C. And if it helps you to remember, you put like a little C for counterclockwise. Okay, when we look at the next one, here you have a center of high pressure. So air is sinking down. It's moving outward. This is where we're going to get hawk. Right? High pressure, outward moving, clockwise rotation. So this brings us to the end of this section. I apologize if there was any issue with the lesson yesterday, but at this time, make sure that you've gone back and filled in any of your notes. I will come around and check that your notes are complete up to this point on Thursday during lab. Okay, so lab day for period 1, lab day for period 7. Friday, I'll do lab day for period 3. Okay? Go ahead and get started on your homework, and have a great day.